Here is a riser sports problem that we solved. We have two variables here, decision variables or decisions to take. A is the number of all-pro footballs and C is the number of college footballs that we will make. And then we had constraints 1 through 5. We also had the non-negativity constraints. The objective here was to maximize the profit, which was 50A plus 40C. We solved this graphically and the optimal solution turned out to be D at the point 1400, 600 with an optimal objective function value of 94,000. Then we went ahead and solved this using solver. Got the same solution, of course. A is 1400, C is 600, and the total profit is 94,000. Now, how did solver solve this problem? Did it use the graph? No, it did not use the graph. It cannot use the graph because let's say if you had 10 decision variables, there is no graph to look at. What the solver did was it used the simplex algorithm. We will try to see what the simplex algorithm does. Essentially, all software packages will implement the simplex algorithm for us to give us a solution to a linear programming problem. Simplex algorithm is essentially the algebraic method for solving linear programming problems. And it is based on the fact that for a linear programming problem, a corner point of the feasible region will be optimal. So therefore, what the simplex does is it only looks at the corner point solutions and it doesn't have to look at the infinitely many other solutions in the interior of the feasible region ever. So then, if it only has to look at the corner point solutions, how many corner point solutions do we have? In this particular example, we have 5 of them, A, B, C, D, E. But in general, we will have a finite number of them. Let's try to get a sense of what the simplex algorithm does by just using the graph that we have. What the simplex algorithm will do is it will first start at one of the feasible corner points. Let's say we start at the feasible corner point B. At B, we are not making any all-pro footballs or college footballs. The coordinates of B are 0, 0. And of course, therefore, B gives us a profit of 0. And since we are not making any footballs, we are not using any resources. And therefore, all the 3 constraints will have slack in them. We have capacity that is spare in all 3 of them. So the next thing that the simplex algorithm will do is it will ask the question, is B optimal? Let's look at the graph. Is B an optimal solution? No, because we can actually make some all-pro footballs or college footballs. Let us say we decide to make all pro footballs. Then we will move away from B towards increasing values of A, that is on the x-axis or the A-axis. Move in the direction where A increases. The second question then is how far can we go? From the graph, it's quite clear that we can go up to the point C. That's the furthest we can go without leaving the feasible region. So if we decide to increase A, we can move from the corner point B to the corner point C, which is the next adjacent feasible corner point that we see on the graph. What if we chose to increase the number of college footballs instead? Well, then we will move in the direction of increasing values of C, that is on the y-axis. How far can we go in that case? Well, we can go till the corner point A to remain feasible. That's the furthest we can go. And after that, there are no feasible solutions on the y-axis. In this case, the profit will increase by 40 per unit increase in C. In the previous case, the profit would have increased by 50 per unit increase in all pro footballs. To summarize, the simplex algorithm does the following. At step 1, it finds a starting feasible corner point solution. In step 2, it checks if this solution is optimal. If it is, then it is done and it will stop and declare the current feasible solution that it is at to be the optimal one. If not, then it will go to step 3, which essentially says move to the adjacent corner point solution, which will give us a higher objective function value. Once you've done that, you now are sitting at a new corner point solution. So therefore, you need to go back to step 2 and ask if this new solution is optimal or not. And then keep repeating till you find the optimal solution and you stop. On the Riser Sports example, here is the problem that we had. We could start at the feasible corner point B00 like we said, where we are not making any footballs and the objective function value is 0. In step 2, we will ask the question, is 0, 0 an optimal solution? Clearly it was not. So therefore, we will either increase the value of A or increase the value of C, which will then help us get a better profit and objective function value. Therefore, we will move from 0, 0 to an adjacent corner point. And then again, go to step 2 and ask the question, is this new corner point optimal or not? And continue like that till we find the optimal corner point.